Hi, it's Miss Molesbury here. Today this video is going to help with, we're still working with radicals, so all of our roots, but we're going to actually perform operations where we multiply them together, divide them, add and subtract them. So at the top of the notes, you'll see a reminder from last class. Remember that a fractional exponent is called a rational exponent, and that's if something's in exponent form or exponential. We can rewrite that in radical form, where the numerator is the power and the denominator is the root or the index of the radical. So you'll see that in this example over here, it's x to the fourth, but it's the cube root of that because of this denominator. So what we're going to find today, we're still going to rely on all the exponent rules from last class. And so one thing to note is that a lot of times it could be easier to simplify in rational exponent form. Or exponential form. And you'll see why here in just a second. You do not have to have like terms to multiply. So what I mean here is we are allowed to multiply if the argument underneath the radical is different, even if the index is different. Like here, we're going to multiply a square root by a cube root, and that's okay. So let's go ahead and jump in. It says perform each operation and extract all roots. That means our answer needs to be simplified. And it says write your final answer in radical form with no radicals in the denominator. So there's a chance we'll have to, at the very end, rationalize our answer like you did in geometry. Okay, so let's get started. A says we have 2 times the square root of x times the square root of x times 5 square roots of x. So the first thing I'm going to do is show you we can put this into rational exponent form. So having a square root is the same as having x to the 1/2 power. So it's 1 for the power and an implied 2 when you see a square root. This is multiplying by x to the 1/2, multiplying by 5x to the 1/2. So we're going to use our exponent rules and multiply together the coefficients. 2 times 5 is 10. And then I'm going to add the exponents on that common base. So 1/2, 2/2, 3/2 is what I get. And then I have to change it back to a radical. So now I can see that it's a square root because of the denominator, x cubed. And we're going to go ahead and see if we can simplify this. So if you leave something under the square root, make sure there are no pairs here. It looks like I do have a perfect square. I could take, this is x times x times x, so I could take a pair out, and it's going to leave 10. I get to take 1x out, and it's going to leave an x behind. So that's because there were 3 x's. I needed 2 of them to take the square root, and the square root of x squared was x. So that's what our final answer is going to look like. We are also today still assuming all of our variables are positive. So if you see any sort of work with absolute value in our solution, it's not necessary. We're assuming all of our variables are positive. No absolute values would be necessary here. Okay, so let's try this again. It's kind of a lot, but we have cube roots here. So first thing I'm going to do is go ahead and change them into rational exponents. So the cube root is the 1/3 power. And so here my only coefficient is 2. I get to add my exponents. 1/3 plus 1/3 is 2/3. And now I have to convert it back to a radical. So this would be 2 times the cube root of k squared. Now there are only 2 k's under the radical, So I can't take any out. I would have to have a group of 3. You also may have noticed, well, wait, couldn't I just multiply these together, the cube root of k and the cube root of k, and made the k squared? Technically, yes, that works if they have the same index, if they're both cube roots. Once we get down to problems like D, that won't work. So I'm going to keep practicing by changing them into fractional exponents so that you don't have to think about if it'll work or not each time. Okay, put a star next to C. You're going to see something similar to it on your assessment for this unit, so let's make sure we can do it. So it looks like I have 7 square roots of h times this whole quantity, 3 square roots of h plus 4 square roots of h cubed. I cannot combine inside the parentheses because they're not the exact same root with the argument. Like this first h is not cubed. So I'm going to go ahead and convert everything. 7h to the 1/2. And then 3h to the 1/2 plus 4h to the 3/2. And I'm going to distribute. So I'm going to have 21h to the 2/2, which is just 1. So I guess I'll write it 2/2, and then we'll simplify. 7 times 4 makes 28h to the 4/2. And here, these divide evenly. I just get 21h plus, 28h squared. And that's as far as I can go. I don't need to convert it back to a radical because there is no radical. Also, if you had just distributed as is, this one would still work out okay. You would have had h squared and the square root cancels. You would have had h to the 4th, and the square root divides that power in 2. But again, I told you I'm sticking to rational exponents, and I am. So let's try D. D says we are going to do the square root of a times the cube root of a. On this one, you must convert them into fractional exponents. So a to the 1/2 times a to the 1/3. And now we know when we multiply two terms with exponents, we have to add their exponents, which means I need a common denominator. So 1/2 and 1/3 could become sixths. So I'm going to multiply the first fraction by 3/3, so it's 3/6. The second fraction would be 2/6, and then I get to add them together to make a to the 5/6, which I then have to convert back to a radical because that's how it wants our answers. So the radical, the root is the 6th root, and it's a to the 5th power. So it's the 6th root of a to the 5th. Okay, let's keep going and see what we've got on the next few. E says we have n times the cube root of 4n times the cube root of 2n cubed. Okay, I'm going to go ahead and convert it all again just because I said I am. If you did want to go ahead and multiply these here, you would be allowed to because their index is the same. So I'm going to have n is to the first. The 4 gets a 1/3 power. The n gets a 1/3 power. The 2 gets a 1/3 power. And what else do we have? The n gets a 2/3 power. Okay, so if we look at our coefficients, 4 to the 1/3 and 2 to the 1/3, since they have the same exponent, I could multiply them and say this is going to be 8 to the 1/3. And then if I go add all of these exponents within, I'm going to put 3/3, so it's 1 plus 1/3 plus 2/3. I'm going to go the long way and say that's 6/3. And then I'm going to go ahead and rewrite it, and simplify it, right? So it looks like 8 is to the 1/3 power. So that's the cube root of 8. Oops, oh, that was a bigger eraser than I meant. And then right here, when you notice 6 divided by 3 is 2, that means you're just gonna have n squared. You're not going to have n under the cube root. And then we can go ahead and take the cube root of 8. So 8, we know that from our parent function table, its cube root is 2. So 2n squared is the final answer here. Again, we could have multiplied these together first and then simplified the cube root because I only saw one type of radical. I saw cube root only, so that would be allowed. Okay, let's keep going. On F, we have 4x to the 4th over x squared. You have a couple of options. It says x cannot be 0 because we know we can't divide by 0. So you have a couple options. If you want to simplify the inside first, we can do that. So I really have the square root. We'll reduce our x's down to 4x squared. And then you can just take the square root like last class. We could also write it as 4x squared to the 1/2. But as we apply that exponent, we're just going to get 2x because the square root of 4 is 2, or 4 to the 1/2 is 2, and then the square root of x squared is x, or if I multiplied the 2 and the half here, I'm just going to get x to the 1st. Okay, so I was allowed to simplify here because both of these were under the same radical. When I look at question G, that's not the case. They're not under the same radical and their index of their radicals are different. So this one, I want you to put a star. You're going to see something similar. We have to put it into rational exponents. So 2a to the 1/2 over 5a to the 1/3, and now we're going to use our exponent rules. So when I have two terms with exponents that are dividing, we know these exponents subtract, but I'm going to need a common denominator in order to do that. So let's turn it into sixths again. 3/6, 2/6, and subtract. So it looks like a is going to be to the 1/6 power, and if I check my 2 and 5, they cannot reduce. So you could leave it a big fraction, you could put just 2/5 in front of your a to the 1/6, but at the end we have to convert it back to a radical. So the denominator 6 tells me this is the 6th root of a. And then again, I could put it all over 5, or I could just use 2/5 as my coefficient in front of the radical. Final answer, done. Okay, looks like H is similar. So I'm gonna go ahead and do H. It looks like we have the 2/5 again, but we've taken this up a notch. So let's go through and see what we can simplify here. So I'm going to rewrite this 2a to the 5/2. I have a 5, and then we've already done the cube root of 8 in the last problem, so I'm just going to make that a 2. And then I have a to the 2/3 since it was squared but under the cube root. Okay, let's see what we can cancel here. It looks like as coefficients, my 2's are going to divide out and make a 1. And then I can subtract these exponents if I have a common denominator. So let's change it into sixths again. Multiply the top by 3, so 15/6. And the denominator has multiplied by 2. So 4/6. So I'm getting a to the 11/6 over 5. Okay, let's convert it back. So it's the 6th root of a to the 11th all over 5, or you could put the 1/5. You could make this whole thing a 1/5 and write it in the front. Now, before I box it, double check and see, are there at least 6 a's, a group of 6 that we could bring out of that radical and simplify it? The answer is yes. So if I bring an a out of that radical, that means I brought 6 of them out, and there are still 5 left multiplying under the 6th root. So this is what my final answer would look like. Whew, it's a lot. And it's going to take some practice. But I promise the ones you're going to see on an assessment, they're not the most difficult ones we're going to do. Okay, I'm going to leave for you if you want to try it. It's more of a challenge level question, and you can go on Canvas and work through it. But I am going to do J. So you will see something on an assessment like J, but probably an easier version of J. So let's go through and talk about it. We have a couple of options. We could either simplify on the inside first and then apply the 1/2. I think I'm going to apply the 1/2 to everything first because it already has simplifying of fractions. That way I only have to deal with my simplifying of fractions once. Again, up to you. It doesn't matter either way. So if we apply the 1/2 to everything, what's that going to look like? We're going to have the square root of 121, or write it to the 1/2 power. My brain applies the 1/2 power better to a whole number, especially one I know is a perfect square, if I write it as a square root to help me simplify. Oh, okay, let's see. I have x to the 3/4 power, and it's going to get multiplied by the 1/2 power from the outside. The y is going to get multiplied by the 1/2 power. In my denominator, everything's going to get the 1/2 power. So the square root of 36, x to the 2/3 gets the 1/2 power. Y to the 1/4 gets the 1/2 power. So we now have, let's see, 11 x to the 3/8, because we're just multiplying fractions, top with top, bottom with bottom. There was nothing I could reduce. Y to the 1/2 over 6 x. Ooh, here I could reduce these 2's. It could be 2/6, or I know that reduces down to 1/3. And y to the 1/8. Okay, I can still keep reducing here my x's and y's, but I need a common denominator. Oof. So let's see, for my x's, I'm gonna do 8 times 3, so I'm gonna use 20/4. So I'm gonna have, let's see, 9 20/4, because I'm multiplying by 3. This one down here is 8 20/4. And then with my y's, I'm going to convert that into into eighths. So 4/8 and 1/8. Okay, almost there. And now I'm going to subtract. So I have 11x to the 1/8. 1/24. Let me erase that. And y to the 3/8. Okay, not a very nice answer. I really should then convert it all into radical form. So it'd be 11 times the 24th root of x times the 8th root of y cubed. Okay, so that was a lot. We had to convert everything to be a rational exponent, multiply by the outside power or apply it to the front coefficients, get a common denominator in order to subtract those exponents, and then convert it back into radical form. I should have said at the beginning of this video, these are not the most fun problems, like at all. At all. We'll turn to the back. We're going to do a couple more that are a little bit more fun, maybe. So let's look at the back. It says, combine like terms if possible and write the final answer in radical form. Okay, so let's talk about what like terms look like with radicals. Like terms have to have the same index, so like square roots with square roots, and the same argument. So like under the radical, in order to add together. So for example, A is a perfect example of like terms. They're all 3 square roots, and their argument underneath the radical is just x and x and x. I'm adding here, so if I have 2 of them, plus 1 of them, plus 5 of them, I'm literally just counting up how many square roots of x I have. I now have 8 square roots of x. That's it. So these had like terms I'm allowed to add. We're not multiplying here like we were on the front. Okay, so the next one, check. I have square root, square root, square root, h, h, h. Okay, these are all like terms. So just combine their coefficients. 7 minus 4 is 3, plus 2 more would be 5 square roots of h. Put a star next to C. You'll see something like it on an assessment. So for example here, these are all square roots. I'm going to go ahead. We could decide if we wanted to simplify on the inside first, like use order of operations. This would be 3 square roots of t times -7 square roots of t. Those are allowed to combine together. Bring down my plus 4t. Now I'm switching gears to multiplication. So multiply 3 times -7 is -21. Think about, I could convert this to t to the 1/2, t to the 1/2. Or as I multiply them, it's the square root of t squared. We should be able to see that that square root and square are going to cancel. So I have -21t plus 4t, which is -17t. So again, if you see the square root of something times itself, the square root will cancel. Or you can convert it back into t to the 1/2 if you want to. Okay, let's do E, because it looks like the last one's a little bit of a monster, but we can do it. So I'm going to go a little bit quickly. You can always slow down the video if you want me to go slower. Or speed it up if you want me to go faster. Okay, so E, and then we'll go over to D. So I have to start by multiplying these. I'm going to rewrite this as 5x to the 1/3 times 6x to the 2/3 power plus 4x. So the first two, as I multiply them, I'm going to get 30. And then I add together their exponents. 1/3 plus 2/3 is 3/3. That's a beautiful, because 3/3 is just 1. So 30x plus 4x is 34x. Okay, so how did I look at example D and see that it was going to be more complicated? Well, I see that it has multiple terms in here, not like terms. It has distributing. It has possible combination of like terms here. So let's just convert everything and see what we get. So I'm going to do 4x to the 1/2 times 2x to the 1/2 minus 3x to the 1/3 power plus 4x to the 2/3. Okay, so the sooner you can get used to rewriting from radical to rational exponent, like the easier your life is going to be. And now as we go multiply, we're gonna have 4 times 2 is 8. And I'm gonna add my exponents. 1/2 plus 1/2 is 1. So that x has an exponent of 1. Then go distribute to the next part. Minus 12, and I'm gonna have to get a common denominator here for the 1/2 and the 1/3. We'll do that in the next step. 4 times 4 is 16, and I'm gonna have to get a common denominator for the x to the 1/2 and x to the 2/3. So keep going. So I'm gonna convert this to sixths again. So 3/6, 4/6 at the end here. And so now I'm going to go ahead and combine these into 12x to the 5/6, 16x to the 7/6. And as you do this, anytime you see an improper rational exponent, it means we're going to be able to simplify our radical. So it means there's more than one group of 6 in this x to the 7/6. Okay, so let's convert it back to a radical, and then we'll simplify. So we have the 6th root of x to the 5th. 16 times the 6th root of x to the 7th. And I'm going to go ahead and simplify this as my last step. 8x minus 12 times the 6th root of x to the 5th. Plus 16, I get to take out an x, which is a group of 6. So there would be one x remaining under the radical. That's as far as I can go. So yes, this is a very tedious process, and it's going to take practice. It has all your favorite things, right? So many fractions in here and working with exponents. But the good thing is next class, the lesson is so much more fun. We get to actually solve, and it's much more practical than what we've been doing. So look forward to that. Don't give up. I promise this unit, this is not the focus of it. So you'll only see a minimal number of questions on assessments over this topic.